Hello and welcome you all for today's fifth lecture on the topic Fundamentals of Thermodynamics from the subject Thermal Engineering. Before heading with a new point, first we will just take a review of all the points that we have seen in the previous lecture. In this slide, I will just discuss the highlighting points from our fourth lecture, which we have already studied. So we have started our previous lecture with flow work. I have already told that this question has been asked in paper many times. So flow work, which is also known as flow energy, is nothing but the work or energy required to advance or to push a fluid against the existing pressure. We have seen that flow work concept is only applicable for the open system, since in case of closed system or isolated system there is no any transfer of mass. So we have also seen the formula for flow work, which was nothing but W, that is work is equal to the product of pressure and specific volume. So this was about the flow work. Then next we have started with zeroth law of thermodynamics. So before starting with zeroth law of thermodynamics, we have already seen the entire history regarding why this name zeroth law has been given. However, for MSBT paper, there will be no any question related to the history of any law. So we will not repeat that part again in this lecture. I will just repeat the statement of zeroth law of thermodynamics. So it states that if two thermodynamic systems are each in thermal equilibrium with the third one, then they are also in thermal equilibrium with each other. So to understand the concept of zeroth law of thermodynamics, we have seen one example in which I have told that we have taken the example of ice and a glass of hot coffee and the surrounding atmosphere. So we have related all these three systems and discussed that how these three systems will attain the state of thermal equilibrium. So I have also told that the zeroth law gives us idea whether the heat transfer will take place or not. So this was about zeroth law of thermodynamics. After this, we have seen what is the law of conservation of energy, which is stated as energy can neither be created nor be destroyed. It can be converted from one form to another. The total amount of energy in the universe remains constant. So here again we have seen the example of a car which was initially placed at a particular height. So when this car is at particular height, then it is having maximum potential energy and minimum kinetic energy. However, if the same car is running down a slope, then at that time this potential energy is converted into kinetic energy. When this car reaches at the bottom, at that time the kinetic energy of that car will be maximum. However, the potential energy at the same time will be minimum. So this was example given related to law of conservation of energy. We have also seen the equation for the same, that is total energy is nothing but it is the summation of internal energy and work as well as heat. So after this law of conservation of energy, we have seen another version of first law of thermodynamics. We have seen the three statements which is stated as follows. The first statement was when a closed system undergoes a cyclic process, then the sum of heat interactions is equal to the sum of work interaction. Again, the second statement for first law of thermodynamics was for a cyclic process, heat and work are mutually convertible. And the third statement was related with the internal energy. So the statement was the change in internal energy is equal to the difference of the heat transfer into the system and work done by the system. So again, for this third statement, we have seen one example in which a container was filled with gas and a piston was placed on that container. So with the addition of heat, we have seen that the container or the gas which is present in the container may expand, and as a result of which we can obtain some work. So we have seen that with the addition of heat, the internal energy of the system increases, whereas work is also obtained due to the movement of that piston. So we are taking work as negative, and since heat is added, it is taken as positive. So with addition of heat, the internal energy will go on increasing, and with increase in work, the internal energy will reduce. Or more particularly, if the work is done by the system on the surrounding, then it will reduce the internal energy. After these three statements, we have seen the limitations of first law of thermodynamics. So in that, I have explained 3 points. That is, the first law of thermodynamics does not give any information regarding the direction of heat and work transfer. It also does not tell whether the system will undergo change or not. And the last point that I had discussed was it does not give any information regarding how much percentage of one form of energy will be converted into another form of energy. So this was all about the first law of thermodynamics, and then we have concluded our previous lecture with the concept of PMM1, which is nothing but perpetual motion machine of first kind. So it is a machine that violates the first law of thermodynamics. If such machine is practically not possible, it is a machine that will produce continuously work output without consuming any energy. So again, to understand this, I think I have given one example related with a engine of a car or bike. So if we consider a perpetual motion machine or if we are relating this concept to that engine, then it will be a machine which is going to produce continuously output work without consuming any fuel. So practically this is not possible. We are not if we are not giving any fuel to the engine, then it will stop to give the output work. So this was all about a perpetual motion machine of first kind. Now we will start with our new point, that is second law of thermodynamics. For second law of thermodynamics, we are having two statements. The first is regarding the heat engine, that is Kelvin-Planck statement, whereas the second statement is regarding heat pump, and it is called as a Clausius statement. We are going to study in detail regarding the concept of heat engine, heat pump, and refrigerator in the last part of this chapter. But for the sake of second law of thermodynamics, we will see what is the heat engine and heat pump. Heat engine is actually a device which converts the heat energy into mechanical work, whereas heat pump is a device which takes work as the input energy and transfers energy in the form of heat from cold junction to hot junction. We will see the statements of Kelvin-Planck and Clausius statement in further slides. So now the Kelvin-Planck statement. Before going to the statement, we should first know that here the two terms are involved, that is heat and work. So we have already studied the concept of heat and work. I will repeat it once again. Both heat and work are having the SI unit as joule, since both are one form of energy and both are interconvertible. However, we have studied that work is high grade energy, as we can convert the entire work into heat, and on the other hand, heat is a low grade energy, as we cannot convert the entire heat into output work. So if we now see the statement of Kelvin-Planck statement, then it states that it is impossible to construct a device working on a cycle that would convert the entire supplied heat energy into equivalent amount of output work. So we can understand the statement. It simply says that it is not possible to convert the entire input heat energy into equivalent amount of output work. So we have diagrams here. In the first diagram, it is shown that E is nothing but the heat engine, and we can see that from the reservoir there is some input heat going to the engine. So heat energy is supplied from reservoir to the engine, and the engine is converting this heat energy into equivalent amount of output work. So practically this is not possible. According to this Kelvin-Planck statement, such type of engine or such type of device is not possible. In the second diagram we can see that there is input heat energy from the reservoir, which is represented by TH. So from this reservoir the engine is receiving heat, and that heat is represented as QH, whereas some partial amount of this input heat energy is converted into output work, whereas the remaining heat energy is rejected to the other reservoir, which is at temperature TL. So this type of machine or this type of engine is practically possible. So from this statement we understand that it is not possible to convert the entire input heat energy into equivalent amount of output work. We will see one example for this Kelvin-Planck statement. So if we consider the engine, that is a car engine or the engine of a bike, then in that case we are providing petrol or diesel in case of car to that engine. So this fuel, that is petrol or diesel, is nothing but chemical energy. So once the chemical energy is fed to the engine, this chemical energy is first converted into heat energy, and later on this heat energy is then converted into mechanical work, as a result of which displacement of the vehicle is possible. However, if we assume that the input heat energy is say about 100 joule, then this entire heat energy is never converted into equivalent amount of work. So it will be partially converted, because we know that whatever the exhaust is given out of the engine through silencer, there will be some amount of heat energy which is rejected to the atmosphere through this silencer, as a result of which the silencer gets heated. So according to Kelvin-Planck statement, it is never possible that whatever the fuel we are providing to the engine, that fuel is entirely converted into equivalent amount of work. Now we will see the other part of second law of thermodynamics, that is Clausius statement. So first we'll see what is the statement. It states that it is impossible to construct a device that operates in a cycle which extracts heat from a low temperature reservoir and supplies it to a high temperature reservoir without any external energy. In simple words, we can say that it is not possible to construct a machine which will transfer heat from a low temperature reservoir to high temperature reservoir without consuming some form of energy. So this is actually given in the statement. To understand this statement, we will see some diagrams. In the first diagram, we can see that the impossible system is shown in this figure, because the heat is given in the direction, that is, it is transferring from cold reservoir to hot reservoir, and such type of system is not possible if we are not providing any some external energy to this system. So a combination of possible and impossible system is shown in second figure. So here in the second figure we can see that a cold reservoir and hot reservoir is given. However, the heat is not possible to transfer from a cold reservoir to hot reservoir, so it is given a cross mark is shown in there. whereas the spontaneous heat transfer, that is if we want to transfer heat from hot reservoir to cold reservoir, then in that case there is no any requirement of external energy. So from this we should understand that if we want to transfer heat from higher temperature region to lower temperature region, then this process can occur naturally. There is no any requirement of for providing some external work to the system. However, if we want to transfer heat in reverse direction, that is transferring heat from a cold reservoir to hot reservoir, then this process will not take naturally. For this we have to provide some external energy. So this is given in the second law of thermodynamics, that is a Clausius statement. Again, in the third diagram we can see how this possible system can be represented in the form of schematic diagram. So again, here we are having a hot reservoir and cold reservoir, and in between these two reservoirs a heat pump is placed. So heat pump is a device which will take input work, and then it will transfer the heat from cold reservoir to hot reservoir. So this is the possible system diagram, because here we are providing some energy, that is external energy, to the heat pump, and as a result of this it will transfer the heat from cold reservoir to hot reservoir. If we consider an example for this Clausius statement, then we can simply consider our refrigerator or air conditioning system. So there what actually happens, if we consider, just say we are assuming the example of air conditioning system, then whenever the AC is installed in a particular room whose temperature is to be controlled, then in that case the what AC will actually do, so it will take electrical energy, which is nothing but our work in the system. So after taking this input work in the form of electrical energy, the AC will extract the heat from that room, which is nothing but our cold reservoir, and it will transfer this heat to the outer atmosphere, which is nothing but the hot reservoir. So in this way the AC will work. To understand again, I have some more examples for this Clausius statement, so that this concept or the statement can be easily remembered. So in this diagram we can see that two buckets are placed at different heights. So if we want to transfer water from one bucket to the other, then always the bucket which is at a particular greater height, from that bucket the water will naturally come down to the bucket which is at bottom. So this will occur naturally. We do not have to provide any external energy for transferring the fluid from the one bucket to the other. On the other hand, if we want to transfer this fluid from the lower bucket to the upper bucket, then this will not happen naturally. So if we want to transfer the water from the lower bucket to the upper bucket, then we must require a pump, so that it will provide some external energy, and then this fluid can be transferred in reverse order. Similarly, the another example given is of balloon. So air will leak from the balloon on its own. It will not require any external energy. However, if we want to transfer the air in reverse direction, that is the atmospheric air to be entered into that balloon, then naturally this will not occur. So for this purpose we have to again provide some or do some work, so that the outside air will go inside that balloon. So this was all about a Clausius statement. We will now see the concept of PMM2, that is nothing but perpetual motion machine of second kind. So it is almost similar to that which we have studied earlier regarding PMM1. So PMM2 is the perpetual motion machine of second kind, which violates the second law of thermodynamics. So such type of machine, it converts the entire input heat energy into equivalent amount of output work. So we have studied this in the second law of thermodynamics in KelvinPlanck Statement, that such type of machine is practically not possible, which will convert the 100% input heat energy into entirely into 100% output work. For this we have considered the example of car or a bike engine. So in engine what we are doing, we are providing chemical energy of fuel. So this chemical energy of fuel is first converted into heat energy, and later on this heat energy is converted into mechanical work. However, whatever the fuel that we are providing to that engine, it is never converted totally into output work, because some part of this input heat energy or some part of this chemical fuel energy that is supplied to the engine, it is partially rejected in the form of heat into the atmosphere through silencer. So this system that is converting 100% input heat energy into 100% output work is practically not possible, and so we call it as a perpetual motion machine of second kind. So this type of machine is practically never possible to construct. So this is about PMM2. Now we will understand the concept of reversible process and irreversible process. So first we will see a reversible process. The process in which the system and surrounding can be restored to the initial state from the final state without producing any changes in the thermodynamic properties of the universe is called as a reversible process. In simple words, if we assume that a system is changing from state 1 to state 2 and again returning back from state 2 to state 1, such that both the systems and the surroundings return to their original condition without affecting the universe, then we can say that the process is the reversible process. But in reality, no such processes as a reversible process can exist. Thus, the reversible process can be easily defined as idealization or models of a real process on which the limits of the system or device are to be defined. They help us in incurring the maximum efficiency of system in case of an ideal conditions, and thus the target design can be set. We can again understand the concept of reversible process with the help of some examples. Like if you consider the example of spring, then as shown in the diagram, we can consider the compression or expansion of spring is nothing but a reversible process. If we apply some force on spring, then it will get compressed, and simultaneously it will also store the applied energy. And when the applied force is removed, it will release back the stored energy. Thus the system nor the surroundings are much affected. However, if we are going for more detailed calculations, then the work for compressing the spring and the work which is obtained by the retraction of spring will be never same. There will be some minor difference in between the applied and obtained work, but still we are neglecting these minor changes, and we are assuming that the process is reversible. Like this, along with the extension of spring, few more examples I will give. That is nothing but frictionless motion of solids, or slow adiabatic compression and expansion of gases. So these are the examples for a reversible process. Now we will see regarding the irreversible process. So the irreversible process is the process that cannot return both the system and surrounding to the original conditions. So again, for this concept we will consider one example of making tea. So for preparation of tea, we will use certain ingredients such as water, sugar, tea powder and milk. So if we assume that our first system, that is the system at state 1, is nothing but all these ingredients which are separate. Now we will mix up all these ingredients and provide some heat, so that the system will change from state 1 to state 2. So our state 2 is nothing but the tea which is ready for drink. Now if we want to bring back the system from state 2 to state 1, so is it possible? So it is never possible, because once the tea is prepared, we cannot separate out all the ingredients from it, such as sugar or tea powder. We cannot remove these ingredients back from the prepared tea. Another example for irreversible process is shown in the second diagram. So this is an interesting example because many students will get confused with this example. So with this example, if the question is asked whether the process is reversible or not, so many students will get confused in this question because the same example we are taking, which is already we have explained or seen while explaining the Clausius statement. So we have already seen that the buckets are placed at different heights, as a result of which water can naturally flow down, that is from upper bucket to the lower bucket. It will not require any kind of external energy for this flow of water. If we consider that there is 20 liters of water in the bucket which is at higher level, and so this water, this 20 liters water will now flow down into the bucket which is at lower level. So for this transferring the fluid, there is no any requirement of external energy. However, now if we want to again transfer back this 20 liters water from lower level to higher level bucket, then we will be using an external source of energy, that is pump. So if we are using the pump and we are transferring this entire 20 liters back to the upper bucket, then most of the student will ask that if we are going to return the entire water, that is 20 liters, back to the bucket which is at higher level, then why we should not call it as a reversible process? So the answer to this question is when the water was coming from a higher level to lower level, then at that time there was no any work interaction. However, there was no any some external work applied to the system. So when we are going to again bring this water back from lower level to higher level bucket, then at that time we are using the pump which will consume energy. So this causes the change in the system and the surrounding, and as a result of this, even though the water is brought back to the higher level bucket, we cannot call it as a reversible process. So few more examples are the water flowing from high level to low level, which just now we have seen. Again, the current, it will move from higher potential to lower potential. Also heat, it will flow always from high temperature region to lower temperature region naturally. However, if we want this flow exactly in reverse order, then in every case we have to provide some external work, and as a result of this, all these processes are irreversible process. So this was all about reversible and irreversible process. So for today we will conclude now, and in the next lecture we will be starting with a new point. So thank you very much.